Here are the opt-out questions for this video. If you can comfortably answer these 3 questions correctly, please join me in the next video. For everybody else, you're in for a treat here as well too. We're going to identify a simple and concise way of identifying the new subnets created when we're stealing host. Present. Now if you're saying, okay Keith, that's easy. 8 represents the fact that the first 8 bits of this address right here that we're looking at represents the network, which also implies that the last 24 bits are all host addressing space. That is perfect. My other question for is the mask in dotted decimal. Fantastic. Perfect. So here's the task I'd like to go ahead and give us. If we needed to create subnets for this topology right here, and this topology has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 subnets that we need to address. And we need to make it all fit inside of the space of 10.0.0.0/8. Everything that you see in this topology has to be within this boundary with an 8-bit mask. So my question for you is, how do we go ahead and do that? Now we've covered this in our video called Stealing Host Bits. And the reason I mentioned that video is that's the first thing we need to decide. How many host bits do we need to steal or reallocate from the host portion? So right now we have 24 host bits. And we need to sacrifice a few of those to create subnets. And my question is, how many of those 24 host bits do we need to sacrifice to create up to 12 subnets? And my friend, to solve that, you simply play the finger game. We also discussed the finger game in the previous video called Stealing Host Bits. So I want you to pause just for a second and calculate right now how many bits, how many host bits would we have to reallocate or give away to the network address space to create up to 12 subnets. Okay, fantastic. So we need to steal 4 host bits. See, 3 wouldn't be enough. 3 would only give us 8 subnets. By stealing 4 host bits, we can get up to 16 subnets, which meets our requirement. So then the question is, what would the new mask be? The original mask is a /8. We're stealing 4 more additional host bits. Those are going to come out of the second octet in this example, because that's where our host bits are starting. And so if we stole an additional 4 host bits and allocated them to the network address space, what would the new mask be that identifies where that new boundary is? Now, if you're saying the new mask would be the old mask plus the 4 additional bits, which would be 12, you are absolutely correct. That's fantastic. And all of that we just did, we have learned in our previous videos in this course. And now, my friends, it's time to identify what the actual subnet IDs are going to be for those new subnets. Now, by stealing 4 bits, we actually are going to have a possibility of 16 new subnets. So we're going to have 4 left over that we're not using because we only need to go up to 12. And that's perfectly fine. But what exactly are those subnets? And to solve that, oh, this is a fun part. To solve that question of what exactly are the subnets for this guy and this guy and this guy, all we're going to do is these 2 simple rules. And let's start with number 1. We are going to, first of all, determine the block size. Now, the block size, and I affectionately refer to it as BS sometimes, just because the shock factor sometimes reminds people to go ahead and look for it. The block size is nothing more than the least significant bit of the new mask. Whoa, Keith, stop the truck. What do you mean the least significant bit of the new mask? Well, if you take a look at these 4 bits that are on, and we're looking at this second octet here, if you look at these 4 bits in the mask, which one is the least significant, has the lowest value? And you might be looking at it and say, well, Keith, it's obvious. If we look at each of these bits, the very least one, the one that has the lowest value, is this guy right here, and that is the new block size. And what I'm going to have you do, if you've written this out, which I would encourage you to do every time you're working with IP version 4 subnetting, these weights, I would have you put a square around that number. So wherever the least significant bit is of the mask, I'd like you to put a block around that value, and that is your block size. In this case, it's 16. If we were stealing 5 bits, it would be 8. If we were stealing 7 bits, it would be a 2. So the least significant bit, we've determined the block size, in this case is 16. Now how is that going to help us? This part is almost magical. What we're going to do is we're going to begin at 0 and then simply add the block size. So for step number 2, in this example, let's go ahead and take 0. Now that's really easy to get to. That is our first subnet, and sometimes it's called subnet 0. So that's our very first subnet, is subnet 0. And then for our next subnet, we simply add the block size. So it's 16, so we add 16 to this. That is our second subnet. And the third one, we're simply going to add the block size again. So plus 16 more is 32. That's our third subnet. And then we're going to add 16 more again. That makes 48. Now don't go doubling these. We're just adding the block size. So take care that you don't start doubling numbers and such, because we're just adding the block size for every new subnet. So that's our fourth subnet. And our next one's going to be 64 for our fifth subnet. Again, we're simply adding 16, and we simply add and add and add and add. And if we added 16 again, it would be 80. So that'd be our sixth subnet. So now as we look at these subnets, what's the problem? Well, they don't really look like subnets, do they? They just look like a digit or a couple digits, and they're not really in the format of an IP version 4 address. So here's how we complete the picture. See this first network of 10.0.0.0? The new mask is going to be 12. All we're going to do is we're going to bring that same network that we started with up, 10.0.0.0. We have the new mask /12, and guess what? That is subnet 0. That is our first network. And that means that in this second octet right here, we haven't added a block size to it. That's our starting point. So subnet 0 looks like the original network with a new mask. For the next subnet, we're going to add that 16. So it's going to be 10.16.0.0/12, and that's our second network. And then 10.32.0.0/12. And that's our third network. And then 10.48.0.0/12. And it's important to put the mask on there so that you can communicate exactly how many bits are being used for the network, and the remainder bits are host bits. And then we have 10.64.0.0/12 and 10.80.0.0/12. And if we continue this process, we would actually get up to a point where we have 16 possible new subnets because of the 4 bits that we're stealing. And the reason I showed you this first without including it inside the IP address is I wanted to show you a process that is simple to follow. And that is, you identify the block size, put a little square around it to remind you, hey, this is the block size. You begin at 0, which is subnet 0, which looks like the major network with just a longer mask. And then you simply add that block size to the appropriate octet. So because here we start with a /8, and we started slicing and dicing in this second octet, that's exactly where we're going to add the block size value. So let's do another example, and I want to do it from start to finish each time so that you get in a rhythm or a pattern of exactly how to do this. Let's say that we want to have this network here, still 12 subnets, and we want to make it all fit in the address space of 10.50.0.0/16. That's our starting point for all of our new networks. We're still going to be stealing 4 additional bits because the actual quantity of subnets hasn't changed. Our new mask is still going to look like this with the dividing line right here, except now we're starting to steal against the host bits, which are in the third octet instead of the second octet. And that's because the 16 bits we're starting with indicate our starting point for the already allocated network bits. So here's what I'd like you to do. I'd like you to do these 2 steps. This is your expert exercise right now. I'd like you to determine the block size based on us using 4 additional bits for custom subnetting. And I'd like you to list out on paper the first 6 subnets that we would be using on this topology. All right, for those of you who are able to do this on your own, that's great. This does take a couple of practices to get the hang of it. So our subnets are going to be right here, determine the new block size, which is 16. So you're going to put a block around that to remind you that that is the block size. You're going to begin at 0, and here's our subnets. They are 0, and 16, and 32, and 48, and 64, and 80, and 96. 1, 2, 3, 4, 5, 6, 7. Okay, so that's the first 7 subnets. Now, what exactly are those going to look like as far as network addresses? Well, the first one is going to be 10.50, because those were already locked in stone before we got there. That's what we were given. And what we're doing is we're stealing the first 4 bits from the 3rd octet. So subnet 0 looks like the parent, I call it the parent network, and it looks like the same exact network except for the longer mask. The mask was 16. We're stealing 4 more bits. The new mask is now going to be 20. The next subnet is going to be 10.50.16.0/20. And the next one is 10.50.32.0/20. And it's just going to continue all the way down. So in a topology diagram like this, we might just say in the documentation that this is the 10.50.x.0/20. And then somebody looking at the topology could say, oh, this is the network 10.50.0.0/20. This is network 10.50.16.0/20, and so forth. This time, let's mix it up. .65.0/24. So that's our starting point, is that 24-bit network. We need to make this all fit. So my question is, when we're given this, the very first thing that you'd have to do is what? What's our very first step? Now, when I look at this, it's like a game. It's like we have to find out some value first. And the first thing we really need to calculate is, okay, how many bits do we need to steal? Right out of our video called Stealing Host Bits. How many host bits do we need to take to create up to 6 subnets? And the answer is 3. So we play the finger game, we determine that we need to take 3 bits, and we are going to change the mask by increasing it by 3. So it would visually look like that. All the rest of the mask for that octet, in this case the 4th octet, would be zeroed out. And the new mask, because we're using 3 more bits, would not be a /24. The new mask would be a /27. So that's all the finger game in calculating what the new mask is going to be and how many bits we took to get there. And now, my friends, it's time for your expert exercise. What I would love you to do is these 2 things. Determine the block size. And then secondly, I'd like you to identify all 6 subnets that we would need for this topology. So pause me right now, take a moment, work through that, and then when you're ready, we'll compare notes. So here's the process that I would go through in solving this. I literally would. If you were watching me sitting at a desk and actually going through this, I would have written out the weights. Now, I do have a lot of it memorized, but on an average day, I would write out the weights, and I'd say, okay, great, my block size is 32, because that's the least significant bit of the mask, the new mask. And I would say my subnets are 0, because that's where we always start. And the next subnet would be 32 more. And the next subnet would be 32 more. And the next subnet would be 32 more. And the next subnet would be 96 plus 32. And we can just add that up. 96 plus 32, that'd be 8. And that'd be 12, which is 128. When in doubt, And the next subnet would be x.x.x. There's no reason to repeat the first 3 octets because we can assume those are not changing. And the last octet is going to be 32/27. And then we have 64/27. And these are our new subnets. So over here, for example, in our topology, we could just write out this is the 25.35.65.x/27. And this is subnet 0, subnet 32, subnet 64, subnet 96, and so forth. The secret, my friend, is all about the block size. Don't get caught up in the actual numbers of the IP address. Get caught up in what the actual least significant bit of that mask is. That will show you the block size, and then you can identify all of your subnets based on the block size. The BS, in this case, is the most important aspect of determining your subnets. So I'd like to do one more with you, and I'd like to go a little bit abstract. Let's say we have a network that is a /16. So forget about the first 2 octets. Whatever they are locked in stone. We are dealing with now the 3rd octet as we're going to start stealing bits. And let's say for the purpose of this discussion that we need to steal 5 bits from host addressing in that 3rd octet. And that would allow us to create up to 32 subnets. So our dividing line is right here. And my question for you is this. What would the new mask be if we're stealing these 5 bits? And what would the first 5 subnets be? And again, it really doesn't matter about these first 2 octets because they're going to stay the same for the entire discussion. It's really all about the 3rd octet where we're splitting and slicing and dicing the bits for subnetting purposes that we need to pay attention to. So again, what's the new mask and what are the first few subnets? Go ahead and pause me and work those out right now. So thank you for taking time to work through that. What is really cool about this process is that it's the same. We're going to go ahead and first of all determine the block size. In this case, the least significant bit is in the position of 8. So that's our new block size. The subnets are going to be 0. Again, we're in that 3rd octet because the first 2 are already chewed up. So our first subnet is going to be the 0 subnet. The next subnet is going to be the 8 subnet. And then we're going to have 16. And then this is for some, this is a little bit of a challenge, but only add 8 again. Don't go doubling. This is just adding the block size, adding the block size, adding the block size. So this would be 24, and this would be 32. And of course, we have another octet out there, so we'd have to hang that guy off as well. And then the new mask, what's that going to be? The original mask was 16. We're taking 5 additional bits. So 16 plus 5 is a /21. And if we had to write out that mask in dotted decimal, it would be 255, which means the first octet is all network. 255. The second octet is all network. That was that way before we got here. And what we've done is we've stolen 5 bits from that 3rd octet. And to represent that, it would be 128 plus 64 plus 32 plus 16 plus 8. Or, and we have 248 already written for us, we could just say it's 248. Any way you want to get there is perfectly fine. It's just math. And then the last octet is all host bits. So the host bits available are the 3 host bits from this 3rd octet plus all 8 bits from the last octet for a total of 11 host bits available. Netting. Secondly, I'd have you go back and take a look at the opt-out questions at the beginning because now, after working through each of these exercises, you should be comfortable and able to answer the questions in the opt-out section for this video. I have had a great time. I appreciate the time we have spent together. I hope this has been informative for you, and I'd like to thank you for viewing.